Welcome to part 2 of this series of data fitting, and in this part we will look at linear models. This is represented by the classical equation y equals mx plus c, the simplest and the most common model you will use. Let's start with the simplest and the most common model, which, as we mentioned, is the linear model. If your data form a straight line, this is what you need. So watch how changing the slope affects the line. A steeper slope means y changes more for each unit change in the x axis. The linear equation is y equals mx plus c, in which m is the slope of the straight line. It tells you how steep the line is. Or you could imagine is that how much y changes for each unit change in x. So a steeper line means a bigger slope. C is the y-intercept, where the line crosses the y-axis when x is 0. You should use this linear model when you have a constant rate of change. So that means you have the two parameters to define, which is the slope and the c, which is the constant, which is the y-intercept. And that should describe a straight line. Use linear models when you see a constant rate of change. So here I just give you some examples to make this is easier to imagine. So as we know, distance equals speed times time. So if you drive at constant speed, the distance will increase linearly. You often hear this term linearly. And what that means actually is the rate is always the same. And the rate, you describe this by the slope. And if you measure the slope at any point in your line, it's always the same. And that is the reason why you define this by two parameters, as we mentioned before. Another example is a business calculation, a classical business calculation, which is cost equals price times quantity plus fixed cost. Likewise, when you want to convert from Celsius to Fahrenheit, this is also a linear relationship. So the rule is any simple proportional relationship where doubling one thing doubles the other, then you should use a linear model. But linear models have limitations. So real-world relationships are often not straight lines. So if you see your data curving, such as this one showing here, don't force a linear fit. Otherwise you'll get poor predictions and misleading parameters. So if your data show curves, that means you need to use different models. Let's see here a classical linear example, which is Hooke's law. When you stretch a spring, the force you apply is proportional to the extension. So if you plot the force versus extension, so you should get a straight line. The slope of this line is the spring constant K. A stiffer spring has a steeper slope. From this simple linear fit, you have characterized the spring mechanical properties. The same principle applies to stress-strain curves in materials testing. Another essential and commonly used linear application is the Beer-Lambert law in UV-Vis spectroscopy. And these experiments are very commonly used in analytical chemistry. The slope equals epsilon times path length. So you build a calibration curve with the standards of known concentrations. You measure their absorbance and you plot the line. Then for unknown sample, you measure its absorbance and you read the concentration directly from your line. So as mentioned, this is quite common in analytical chemistry. So the Kissinger method determines activation energy from DSC, differential scattering calorimetry, but it only applies to kinetic events, not melting. Melting is a thermodynamic transition with a fixed temperature. So any heating rate shift is due to the equipment thermal lag, so not a reaction kinetic. So in this case, Kissinger method does not apply. In this case, for the demonstration of linear fitting, Kissinger is used for processes with an energy barrier. Most commonly is the thermal degradation in pharmaceuticals. As the drug is heated, there will be of course a chemical decomposition, and that appears as a peak in the DSC. And in many cases it comes out endothermic because it will break bonds and because dehydration, decarboxylation, or because of the volatile components are released. And the way this works here, as you can see in the plot, the DSC is going to be used to run a sample at different heating rates, and in this example from 5 to 20 degrees per minute, and you record the peak temperature. Faster heating rates will lead to shifts in the peak to higher temperature, and the reason of this because the reaction has less time to proceed at lower temperatures. So using the Kissinger equation showing here, a plot between the log normal beta, which is the heating rate, divided by Tp squared, that will versus the 1 over Tp squared, it gives you a linear relationship. And the slope of this line is the activation energy. So the beauty of this relationship, the activation energy can be used with the Arrhenius equation to estimate degradation rate and predict shelf life using these accelerated studies. So this can be used in conjunction to estimate stability of pharmaceuticals. The same method can be applied to other events such as crystallization, polymer curing, and other solid state kinetic processes.